Hi everyone, and welcome to the very last video within the Peer Club R series, at least for this year. As promised, today I will show you how you can develop your own function to check the normal distribution of your data, including the plots and also the summary statistics. And we will today be using functions, not many, but a few, and I will at least show you how approximately a function should look like. But we will definitely be using a loop at the very end, so stay tuned for that. I think the entire script is very useful, not only because it's giving you this one way of checking the normality for many different data groups, but also because I've included a few more bits and pieces in terms of programming that you might find very interesting. So let us start. I have already prepared the script for this to avoid live coding, which usually just takes a little bit of time, and to avoid cases where I'm not prepared for some errors. So we're first going to load the packages that we're going to need today. First, we need ggplot for the plots that we're going to be creating, then dplyr and tidyr for reorganizing the data and calculating the summary statistics, cowplot, which we will use at the very end to combine our plots, and then palmerpenguins, which we are going to use as the dummy data set for today. Okay, so first we can load the dataset penguins and look at it quickly. So we see here we have a few columns, which are species, island, and then a few measured variables, and then we have sex and the year. And we can also check the structure here. We see that species and island are a factor that has 3 levels. And then here sex is a factor with 2 levels, and year is an integer. And I can tell you there are 3 different years, but for now we're going to ignore that. And then, as I said, we have 4 measured variables here. Okay, so first we're going to check the sample size for each species and each island, and also each sex. And we see here that the species Adelie is present on all 3 islands that are in the data set, while Chinstrap is only present on the island Dream, so both for females and the males here, and Gento is only present on the island Bisco, both for females and the males here. This is something that we have to consider later. So in the next line, I will first remove all cases where the sex was not determined. In this case, we just can use the function filter from dplyr and then filter all data that is not NA. Okay, so is NA is checking if there are NAs, and if you include an exclamation mark, that is exactly the opposite. Okay, so we're just removing all NAs here. And in total, these were 11 observations that we removed from the dataset. And also I've used another name now for the object rather than using penguins. The first reason is so that you do not ruin your original data set. And second reason is just because DF is so much more shorter than penguins, and it will just save us some typing afterwards. And then in the next part, and this is nothing that is really important, but for the for loop, it's going to be very useful. What I want to do with this data set is to gather the entire data set from being wide into long, so that each of these columns that have measured variables are now going to be placed below each other. And I've already showed how to use gather here. So we're going to use the key, which we're going to call variable. That's going to be column containing the column names from the original data set. So it's going to be bill length, bill depth, and so on. And then value is going to be the actual measure of this variable. And we want these 4 columns to be gathered together without gathering together species, island, sex, and year. So these should remain the same, and we're only gathering these measured variables here. Okay, so if we do that, and then just quickly look into the data set, we see that it's this how it now looks like. Okay, so we have variable and value here. So these are the 2 new columns. And we see here that variable is just labeled with the name of the previous columns, and here are all the measured values. Okay, so now already to statistics. We can check the normality statistically, and what I will do first here is that I'm just going to use one single variable that has specific conditions. So this variable should be the bill length from the Adelie females that live on the island Torgerson. Okay, Just discovered a typo, sorry for that. Okay, so how to extract this data? There are different ways, and I'm going to show two options. So the first option is to use filter and then specify which variable you want, which species, which island, and which sex. And we can do that. And we will see that the actual output is a data frame. So if you look into your environment, you see that dfx is a data frame. You can open it here. So that's a data frame. So if you want to assess our data, so the actual value, we have to use the data frame name and then $ and value. Okay, so that looks like this. The output of this second option, however, is going to be a vector. So what we're going to do is that we're using basically the same conditions as here, but we are going directly into df $value. So we're going into the original data set, into the value column, and we are basically only selecting the rows that fit to these conditions. Important here is that you every time have to add df $, so that R knows to which data set this actually refers. You do not have to do it here above, because you're using filter and the pipe operator here, which automatically tells R that you should apply filter on everything that is inside df. Okay, so if we do this here, we get a vector. So we see here in the environment that variable.x is here in the part for values. So this is just a vector and looks like this. Okay, good. In general, you can use both for later, but I will just first stick to variable x, just because it's a little bit easier. Okay, so first thing that you can do, and there are different opinions if you should, and if this is the correct way to go with, you can use the Shapiro test. So this test is basically comparing your data to a normal distribution. That means also that a p-value that is below 0.05 would in this case indicate that your data is significantly different from a normal distribution. So here, differently than usual, what we're actually aiming for is a p-value above 0.05, okay? So when we now just run this, so it's just Shapiro test and then the variable x here. And we see here that we get a p-value of 0.27. So this is above 0.05. So we can say that our data is normally distributed. If you want to extract this p-value to use it for something else later, you can basically just save it this way. So you just use the $ and then p.value and save it into an object. And then if you look at the object, it's giving you just this value for the p. Okay. However, as I've explained in one of the previous videos, there are also other rules that can help you to decide if your data is actually normally distributed without having to run the Shapiro test, because as I said, there are different opinions if you should really use the Shapiro test. So some of these rules were that the median and the mean of your data set are equal. Then the second rule is that the mean is larger than the variance, although here, as also mentioned before, I do not really have a source for this. So I will, for now, ignore this part. And then the third rule is that at least 2/3 of the data should lie within mean plus minus one standard deviation. There is also the empirical rule that I mentioned the last time, which says that, again, approximately 68% of the data should be within mean plus minus one standard deviation, and approximately 95% of the data should be within mean plus minus two standard deviations. And the third part of this rule is that approximately 99.7% of the data should lie within mean plus minus three standard deviations. Okay, we're not going to test all of these. We can currently just stick to at least 2/3, but we're also going to calculate the proportion of the data within mean plus minus two standard deviations. Important for all of these is that you use na.rm equals true, which means na remove equals true. This way, you're making sure that all NAs are removed when the calculations are performed. Okay, good. So we can first calculate the median, the mean, the variance, and the standard deviation, and each time just assign them to an object and just give them names that make sense. In this case, just median, mean, var, and SD. And if you're using the semicolon here and just add variables after each other within one line, and then just execute this line, it will just show you all of these variables in the console. Okay, so you can already see here that the mean and the median are very, very close. So we can already speculate that the data might be normally distributed, but we also know it from the Shapiro test. And then now we can check the proportion of the data that is between mean and one standard deviation. So for this, I am taking the length, okay, of all the data that, as I said, is between mean minus one standard deviation and mean plus one standard deviation, okay? So variable being larger or equal to mean minus standard deviation and variable being smaller or equal to mean plus one standard deviation. And then I'm dividing this by the actual sample size of the variable. Here also accounting for the fact that you might have any NAs in your data, and then multiplying this by 100, okay? And in the second line, I'm basically doing the same, except that here we're looking at mean minus 2 standard deviations and here mean plus 2 standard deviations, okay? Good. In both cases, we get something that again tells us that the data is probably normally distributed. So we get 66.67% for the data that lies within mean plus minus one standard deviation. And we get 100% of the data that lies within mean plus minus two standard deviations. I would say that 100 is not usually something that you would get, but it can occur. It really depends on the distribution of the data, obviously. But in this case, I don't think that we have much to worry about, at least from the summary statistics that we've calculated so far. Okay, so in the next part, I will just show how to combine all of these values together to have basically a table of summary statistics if you want. So in this case, I will first define a variable label, which I will just call bill length from elderly females from the island Torgerson here. And I'm just going to run this quickly. And then I'm basically just going to make a data frame. This data frame will have the column variable, where this variable lab is going to repeat it 8 times, because I'm going to add 8 other summary statistics into this data frame. So the next column is going to be the parameter. And here are just the textual labels for each of our summary statistics. And then we're going to have the third column called volume. And here are all the summary statistics that we're interested in. Okay, so if we just run this and then look into it, then we see that this is the output. Okay, I know this looks a little bit long, but at least we have all the information that we need. And then we have each parameter here, and then we have each volume. Okay, and then you have a data frame that you can also export if you want, or you can copy paste it somewhere or similar. Okay, now we can check the normality graphically. What you can first do is just to make a really easy, simple histogram of your data using base R. And this looks like this, okay? You've probably seen these all over the place. I've started using these whenever I started using R. So these were one of the first plots that I ever made. However, we have developed and R has developed and we have cooler packages. So now I'm using ggplot for everything. So in a few seconds, I will show you how to build a histogram using ggplot. First, one thing with ggplot is that you can't use just a vector as your data input. I've tried. So what you can do, even if you only have one single variable, so if you only have one single vector that has all your volumes inside, you can basically just turn it into a data frame, okay? So you at least have to have a data frame with one single column, which is then your variable that you're using within the ggplot, so that ggplot really works, okay? So the way you can do that is basically just using the function sDataFrame and then wrapping it around your actual variable and then assigning this to an object. I'm going to call this object df_x. So it's similar as before. Before that, we had df.x. So that's the data frame that has all other information about each of the values that we are looking at. And here I just really want to have a data frame only with this one column that is going to be called variable x. Okay. And if you now look into this, so it's really just one single column here. Okay, but we need it for ggplot. Okay, we can start building the histogram. If you're plotting a histogram in ggplot, there are 2 options that you can use. You can either specify the bin width, or you can specify the number of bins. I'm going to show both. So in the first case, I'm going to specify the bin width to equal 0.5. And then we get something like this. Looks already fine. We see this huge gap here, but this is something I'm going to be discussing later on. And then here in the second option, we are going to set the number of bins equal 10. And we have this here. Also looks totally fine. However, the thing is that if you're going to use the bin width, this will very much depend on your data. You can definitely use it, but you will see that the bin width depends if your data is in a range of, I don't know, 1 to 10, or if you have values from 1 to 100, then obviously you will have to adjust your bin width. If you want to use this function for many variables at once that might be in different ranges, then I would definitely suggest rather using the bins and just taking a number that you think should fit. And this number obviously then again depends on the data distribution and also on the sample size. So it does not make sense, for example, to take a number of bins that is larger than your actual sample size, right? So also again, a parameter that you have to play with a little bit. But in this case, I would definitely recommend to first stick to the number of bins, okay? So what we're going to do is that we're going to now use the same plot as here, and we're going to assign it to an object because we want to reuse it afterwards, and we want to add a few layers to this plot, okay? So again, we're running this. I will quickly show this, how it looks like. So again, it's the same plot as we just had it, okay? Good. So next, we will add the density curve, okay? So for this, we're just using the ggNorm density here. I've specified the color here and the size. And then if you run this, then we see this here. And this again shows us that apparently the distribution of our data is bimodal, okay? And we will talk about this later as well. In the next part, I'm going to add a density curve that basically represents the normal distribution, okay? So this density curve is plotted using the function dnorm, which I've already shown in one of the previous videos. And it will just take the mean and the standard deviation of your actual data set, and from that plot the optimal density curve, assuming that your data is normally distributed, okay? And now if we do that and look at the plot, we see here this green line, okay? So the green line here is representing the density curve of the normal distribution, and the blue line is representing the actual distribution of your data. Now we can also add the mean and the standard deviation to our plot. And this you can do using the ggNorm V line. V stands for vertical in this case. And because something is vertical, you need to specify the x-intercept. Okay, so that's all you have to do. We're going to specify the x-intercept here. We are first going to plot the mean. It should have a red color and have a little bit higher size, so be a little bit thicker. And then we're going to plot mean -1 SD and +1 SD, and then mean -2 SDs and +2 SDs. And we're going to just adjust here the line type. So for 1 SD, the line should be dashed, and for 2 SDs, the line should be dotted. And all of these lines should be a little bit smaller than the actual mean line. And if we now look into the plot, that's how it looks like. Okay, cool. We're almost done. There is one more thing that I wanted to discuss, and it's this bimodal distribution. I have so far not implemented this into the function, and I probably will not do so because we do not really often talk about mode. And mode in this case, per definition, is a value that occurs the most often in a data set, okay? And I think that using the mode would actually tell you if you might have a bimodal distribution, for example, okay? As I said, I will not implement it into the function, but I will still show you how to calculate the mode and how to understand it and how to work with it. Unfortunately, R does not have a function to calculate mode. Funny enough, R has a function that is called mode, but it's a completely different thing than what we really want to have, okay? So as I said, mode per definition is the value that occurs the most often in a data set, okay? So what we can do is basically count the number of occurrences of each of our values within the data set, okay? We can easily do this with dplyr, so we can just take the data set. We're now going back to the actual data frame here. Okay, so you take the data frame X and then you're grouping this by your value. Okay, so for each value you want to have a count, and then you summarize this, and you just create a new column here, which we're going to call count, and this should take the length of your value. Okay, so it's going to group your values by value, basically, and then just take the length of these. Okay, and if we run this and then also look into it, I'm just going to put this into the console. We see here that we get all of our values, and then we get the counts. Okay, and we see here that there are two values that have the count of 2, and we are still missing 12 more rows. Okay, but we've already seen this, and mostly you will probably get something like this. You will have a lot of ones, and then in between you might have count that is 2, 3, or 4 maybe. Okay, what you then can do is to use the function which max here that will take the counts, look for the maximum count, and then give you the value. Okay, so we're going into the actual value here into the column, and then searching for the row where the count is maximum. But we know already that we have already here 2 values that have a 2 as the count. So this might be a problem. We don't know about the entire data set, but we will see what happens. Okay, so this here tells us that the actual mode is 36.2. So if you look here, that's one of these values that occurs twice. Okay, so this is obviously not giving us the correct answer because it's only giving us one single mode. Okay, what we can then do is basically, rather than using which max here, we can just use the slice max that also comes from dplyr, and then apply this to your count data frame and your variable count. And if you look into that, this will give us 2 rows of data. Okay, so it's giving us the data point 36.2 that occurs twice, and 36.7 that also occurs twice. However, if you look into our plot, we do see that this is probably somewhere here, so where the first peak is, but we still have no idea about the second peak, right? Okay, so just keep that in mind for a second. Instead of doing this manually, we can obviously also write a function that will do this for you, okay? And now we will introduce, for the first time, writing functions. Okay, so I'm going to call this function find mode. And what you only do is that you basically write function here, and then you use parentheses and then the input that you want to have, okay? In this case, we're just going to have a variable x, right? And then you open the curly braces, and you're closing the curly braces at the very end, so we see it here. First, in this case, you're going to make sure that the dplyr package is actually loaded. What you can do is, if you use this part here, so I'm just going to copy paste this. So parentheses and then dot packages and then again parentheses. This will tell you which packages are currently loaded. Okay, and then you just have to check if this dplyr package is in your actual loaded packages. Okay, if this is not the case, okay, so this is why I'm using the exclamation mark here. So I'm just checking if this package is not in already loaded packages. And if this is true, okay, then we're calling this package by using library dplyr. Okay, so that's the first thing in the function. And then the same as we had it before, we are first making a data frame out of the variable, because this only works if your data is actually in a data frame. Okay, and then we're again just creating this count.x data frame by grouping our values by the actual value, and then summarizing the counts by taking the length of these values. And then here we're using return to specify which of these objects we want to have as the output. And as the output, we just want to have the actual mode, right? So again, here we're just using the slice max, okay? So this is now within the function. And then if you want to use this function, you first have to run it. And the best way is, again, just to put your cursor somewhere in the first line of this function, okay? And then you just run it. So it's just control and enter, okay? And now you can use it. So this function should now appear somewhere, yeah, here. It appears in your environment, okay? So you see here that functions has now the find mode function in here. And the only thing you have to do is just use find mode, and then into parentheses, you can put your variable. Okay, and we get exactly the same output as we had before. Okay, just to make sure that this also works when we remove the count x, right? We can just do this again, and we see that also works. Okay, perfect. Good. There is also a function from Stack Overflow that I found. And here they're using the density of x first, okay, and then looking for the x value where this density is the highest, okay. And as you might expect, this is going to give us a different result. So this is just a function. And then if we use this function now on our variable x, we get a value of 39.16. If we now look into the plot, you can see that this value is exactly here where this second peak is, okay? You might not see perfectly here, but if you would plot the data a little bit differently and just change, let's say, the y-axis range here, you would see that this peak in general is just higher than this left peak here. And this is why when you're plotting this as a density function, you're getting a mode that is here, okay? Honestly, if you're asking me now which of these methods is more accurate, I would just say both. You would definitely need both of them because especially in this case where you get two different results, okay, this might already indicate that your data has a B-model distribution, okay? So I would definitely try both. Obviously, you can also just plot your data, but if you're avoiding plotting or if you just want to have another, but if you're not plotting the data and you just want to have the summary statistics, then I would definitely also check for the mode and use both of these functions. Okay, back to our plot. As I said, we will not include this into the plot, but I just found it important in this case to quickly talk about it. What we're now only going to do is add a few bits and pieces that are just going to make our plot nicer. So I'm first going to change theme into theme classic. I will just quickly run this without actually running the entire code. Okay. So as you see, this is just changing the theme by removing the gray background. And we see here, we only have the Y and X axis, and we have the numbers here that are now in gray. This is the only thing I do not really like about this, but you can change all of these small things. So what I'm doing here is that I'm first of all changing the plot margin a little bit. This only has to do with combining the plots afterwards, but it's something that you should not be worrying about too much currently. And then I'm increasing the size for the y-axis title. It should now be 14. And using the margin here, I'm just telling R that I want this y-axis to be a little bit further away from the actual plot. Okay, so this way it's all kind of like really packed together. Then I'm increasing the size of the text on the y-axis and changing the color in black. And here I am entirely removing the axis title for the x-axis, okay, and the text and the text and the line, okay? I'm removing basically everything. And the reason I'm doing so is because later on we want to attach the box plot directly below the histogram, and we want to just use the x-axis of the box plot for both of them rather than having two x-axes, okay? And then in the last part, I'm just increasing the size of the plot title. And then in the last part here, I'm adding the labels. So Y should be density with an uppercase D, and title should be normality off. And then we're including here the variable label that we've already specified sometime before in the script. And I'm adding here a \n for enter, basically just to make a bit more space. You could also use the margin here, but I was a little bit too lazy for that. So you can also do it this way. Okay, if we now run the whole thing and then plot hist, then we see that we're already done. Okay, so this is all that we want to do for the histogram. You can still, as I said, play around a little bit with the bin width or the number of bins. So there are still other options how to improve this plot, but I think that for now, we can be pretty satisfied with what we have. Okay, so now we can move on to the box plot. As I already mentioned, we want to combine the box plot and the histogram by just attaching the box plot below the histogram. So we have to make sure that the range on the x-axis is equal between both of them. Okay, so now that we already have the histogram, we can use the function ggplotBuild to basically get the entire table full of parameters and values and everything else that defines the actual plot. Okay, I will just quickly show how this table looks like. Okay, so it looks like this. So there is a lot of stuff inside that is basically defining your plot. Okay, you can maybe look into this when you have a little bit more time. The important thing that we want to do here is basically to go into data, okay, and then extract the xmin and xmax, okay, and save this into xmin and xmax objects. In this case, these are just values basically, and we see that xmin is 32.87 and xmax is 42.68, okay, good. I can tell you that this is easier than trying to adjust the x-axis first and then using the same range in the box plot and so on and so on. It's a little bit tricky because the way the histogram is built, it might be that your bins go a little bit outside of your specified ranges. So I would say that this way here is the safest. Okay, good. Now we can start building our box plot. So for the box plot, it's really easy. You just need your data, and usually you would have different groups. So for example, for the X, you would have the groups, and then for the Y, you would have the actual values, and then you would get those vertical box plots. In this case, you want to have a horizontal box plot so that we can attach it below the histogram. So we're just going to specify Y to be 0. It can be any number, it doesn't really matter. It just has to be a number. And we are going to specify X as the variable X, okay? And we want this ggNorm to have a dark blue outline, and the size of this outline should be 1. And here I specify that the outliers should not be plotted by just specifying outlier shape to an A. And the reason is because I want to add the row data. If you are adding the row data to your box plot, but you do not specify this, then you might get into a problem that you're going to have the outlier and the row data plotted. And if you're using a jitter to basically jitter your data around the middle of the box plot, then you might have these points occurring twice, okay? So that's why I'm using this. If we now look into this, that's how it looks, okay? Really easy. I already said that I've suppressed the plotting of the outliers, and now I want to add the row data. So to do that, you can just use the ggNorm, and I've set the size to equal 3. I've also adjusted the colors here. I'm using alpha to make these points a little bit transparent. Stroke is specifying the size of the outline of your points. And position jitter is basically telling R that your data should be jittered around the middle. This way you make all of your points a little bit more visible rather than having them only on one single line, okay? And if we now quickly do that, then we get this as the output, okay? Good. And just note that I've used the 0.2 for the jitter height. This is one of the parameters you might want to adjust manually, or something where you might want to choose it if you're, for example, writing a function where you have this. So I will show you how to implement this into the function. Okay, now we can make the box plot a little bit nicer, same as I did before. And now the box plot looks like this. I've here removed the y-axis, so there is only the line, but there are no labels or ticks because we don't need it here, right? And we see here that we have this x-axis here. However, we have not yet specified the scale of this x-axis. So this is just automatically done by R. However, we want to have matching x-axis with the histogram. So that's why here we now have to add scale x continuous, and then we can add the limits, and these limits should be the xmin and xmax, okay? And then we can plot the box plot, and then it looks like this, okay? Good, now we're done. And if you want, you can now combine the two plots, okay? So we're going to use the function plot grid from the cow plot, and you only have to specify the name of the two plots. And then we want to have them in one column, so they should be below each other. You want to align them vertically, and because the box plot obviously should just be like a small part of it, I've specified here the relative height of the box plot, okay? So the relative height here of the box plot should be approximately 1/3 of the histogram. And if you run this and look at it, then we get this, okay? This looks really cool. There is another way of doing this where you can basically completely forget about adjusting the axes. The way you could do this is just to add the boxplot as another layer on your histogram. However, if you're doing this, you would have to go into the negative part of your y-axis. So you would have to specify something like minus 0.1 or minus 0.5 or something. And this depends on the actual range of your density. So we could have included this into the plot as well to basically tell R that it should give you the maximum density and then, for example, take, I don't know, 1/3 of this and just add the box plot below that, where this 1/3 basically intersects with the y-axis. We could also do that, but I just thought that this way it's a little bit easier and it still works. Okay, good. Now we can move on to the QQ plot. The QQ plot, so the quantile-quantile plot, is really easily done in ggplot. You basically just need to specify within the aesthetics here that your sample is your variable x here, and you specify here your data set, and then you use the stat QQ to get the points, so the quantiles, and you specify here the stat QQ line to basically get the line. Okay, and I've changed here the colors and so on. And then if you run this, it looks like that. So we already have it. That's already almost done. The only thing that I'm still going to add are a few bits and pieces regarding the aesthetics. And if you do that, then we have this much nicer plot. And again, in the title, we also have the variable label with all the information that we need. Okay, cool. So we're done with that. We're really fast today. The last element of the function should be the summary stats text. We can either add this text into the actual final figure that we are including as the output of the function, or we can just print it to the console. Okay. One thing that you might want to do is to adjust your p-value a bit. So either you print your p-value just as a number as you have it, or you specify how this p-value should be rounded, depending on how many digits you have. However, with very low p-values, this might get a little bit tricky. So I find that it's totally sufficient to just stick to the different significance levels. So if your p-value is below 0.001, then your p label should just say p is below 0.001. And then if your p-value is between 0.001 and 0.01, okay, so just that part, then the label should be p below 0.01. And if the p-value is between 0.01 and 0.05, then the label should be p below 0.05. And if your p is above 0.05, then the entire text should just say p equals, and then it should give you the actual p-value rounded to 3 digits. Okay, good. So now we can run all of these. So you can see that I've already included these into the if statements, okay, because then we can just use this if statements also for the function. That's why I'm showing all of these small bits and pieces that probably you could have just done also manually. But I want to make all of this as general as possible and also as automatized as possible, so that you learn how to avoid specifying everything manually by yourself and just writing everything in a way that you can use it for many different things at once. Okay, good. So now what we can do is basically to run through all 4 of these. And I'm just going to show the values. I think it should appear somewhere in the values. Okay, so if you run this once, nothing happens. If you run this again, nothing happens. If you run this again, nothing happens. And if you run this the 4th time, then we see here that we have the p lab. Okay, and this is because our p-value from the Shapiro test was above 0.05. So this is why only this part here is going to be executed, because this is the only case in this statement where this part here equals true. Okay, good. And now that we have the p-value here, we can just take everything else together. So it's just a long chunk of text. And every time I use the \n, it just means that R should print the next part in the next line. Okay. And we're basically here just pasting the text that should be printed plus the actual value. Okay. I'm not going to explain this into detail. You can just look into this in peace whenever you're going through the script. So we're just going to save this here. And then you have to use cat to print this to the console in a nice way. And what I've also included here, and the only reason is because we are going to have this in the function later on as well, is that I first want to have two empty lines, and then I want to have a few dashes, just basically as a separation. And then again, two empty lines, and then I want to have this whole part with the summary statistics by first saying that this is the summary statistics for a specific variable, and then again having two lines, and then the entire text, okay? If we just quickly run this, then this is what we get. In this case, for us, it doesn't really matter if we have all of these spaces here and the empty lines and the dashes. So if you now imagine that you're running a loop for multiple variables in multiple groups, then you're always going to get this text in basically text blocks just below each other. And then it's definitely useful to have a few empty lines and maybe a dash line that is just separating those text blocks, okay? What you can also do is to make a ggplot that has only this text inside, okay? And the way you do that is basically that you just call ggplot without any values, anything. Then you use annotate, and then you specify the text, and also x and y also do not really matter how you specify them. And then you just say the size of the text, and as label, you use exactly the summary text that we have here, okay? Again, this is very important to have the \n here so that every time you have each of these lines in a new line. And then you use the team void, and this removes all axes and everything else, okay? If we quickly run this, then we get this plot here, okay? Cool, now we're done with all four plots that you want to have, and we just have to arrange them. So if you want to have all four plots arranged, so the histogram with the box plot below and then the QQ plot with the text below, then you can just do this here. So we already have plots 1. So this is already the plot that combines the histogram with the box plot. And now here I'm combining the QQ plot with the text plot, again into one column, just in the sizes as they are. And then I'm just taking these two already combined plots, okay? So histogram and box plot and QQ plot and the text, combining them again into a big plot, okay? In this case, I want to have them in two columns, so next to each other. And if you run this and then look into that, then we get this as the result, okay? And this is already it. So that's the actual output that you want to have afterwards in the function, okay? We've done everything now manually from one variable, but this is going to be the output from the function that you can run for multiple variables at once if you're using a for loop. Okay, and if you now do not want this text to be plotted within the figure, because you rather want to have the text either saved as a CSV file, or you just want to have it like printed to the console because you do not find it that important, because most of these things are already kind of implemented into plots as well, okay? Then you can just do the following. I'm going to create an empty plot, which is just, again, ggplot and team void, okay? So that's an empty plot. And then combine the QQ plot with this empty plot and just adjust the relative height of this empty plot to be just 1/5 of the QQ plot. And then combine this again into all plots. And if you look into this now, then we see that this normal QQ plot has approximately the size of the histogram. So that's why I picked these relative heights. And then we have some space here, but it doesn't really matter, okay? And that's already it. So these are the two figures that you can get as the output. And you can now just use the all plots to save it then as a PNG or as a PDF or TIFF, or use it for whatever you need. Okay, good. Okay, so now we're done with this, and I will quickly show you how you put all of this together into a function. I will really do it in a very quick way to keep this video as short as possible. So take a deep breath before you start with this, because I know it's a lot. Okay, so this is now another R script, okay? So I'm using another R script to basically write my function, and I'm going to give a name to this R script. So in this case, it's just function ggNorm, and I'm going to call the function from the script within my actual script I'm working with, okay? Good. So this function, as I said, can be defined by just giving it a name first. So we're going to call it ggNorm, and then we are using here the assignment operator, and then function, and then within the parentheses, we have all the input that you want to have in the function, okay? First, it's just x, that should be the variable, okay? Then the variable lab, That should be the label, like the bin length in millimeters and so on and so on. Then there is the bin width and the bins. I'll specify them here as null, okay? If you want to change them into something, you basically just have to write bins equals and then you add a number or something, okay? And I will show how this is afterwards used in the function itself. And then jitter, that's the jitter height that I was talking about earlier. I'll specify this already to 0.2. So if you're okay with 0.2, you can just run the function without even writing jitter, okay? Because it's already the default in the function. And I've specified here print equals true. In this case, it means that the text should be printed in the console, okay? If you specify this to false, then the text is not printed into the console and it's instead printed into your actual figure, okay? I have not implemented both because I just found that it's a little bit too much, but we could also do that if you want to, okay? So if you need to change any of these here, then you have to specify this specifically. But if you're okay with the text being printed into console, and if you're okay with jitter being 0.2, then you can just leave them as they are. Do not even have to mention them afterwards in the function, okay? Good. So first part in the function is that there are 3 packages that we need, which are dplyr, ggplot2, and cowplot2, okay? So we are just here making sure that if these packages are not loaded yet, that they all get loaded, okay? So each time with each if statement, we're checking if the package is part of the packages, and if not, then we are using library here to call the package, okay? Good. Then next, because x can just be a vector, okay, we are here making sure that we are transforming this vector into a data frame, and we're calling it data here, okay? And then we are first calculating the Shapiro test. You can also use data $x here, but you don't have to because you already provided R with your actual variable, okay? The only reason we're doing this is because for ggplot, we need a data frame rather than just a vector, okay? So we are running here the Shapiro test and then extracting the p-value. And then the same as before, we have this if statements. Just going to change this quickly, that are checking for your p-value, okay? And then depending on the p-value, defining a p-label. Then we're calculating the summary statistics here, okay? So median, mean, var, and SD. Note again that here we're just using x, okay? So it has to be exactly the name that you have above in your function as the input, okay? So using x here, so it doesn't matter if your variable has any other name. Your variable does not have to be called x. It can be called anything. As long as you write in the function x equals, and then blah, 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 you'll be fine. Also, if you know the order of the variables, how they should be in the function, so in the function input, you can just also put your variable inside without specifying x equals, okay? So they're small things, but you will learn how to do all of that. Good. So we have the summary statistics here. Then we're calculating the percentage of data within mean plus minus 1 and 2 standard deviations. And then we are getting everything together into the summary statistics. And then we're here plotting the histogram. And here comes the interesting part. So as I said already before, currently bins and the bin width are both defined as null. So they're not defined at all, basically. If you leave it like that, okay, so if you just do not specify one of them, but you specify the other, so you always have to specify one of them, right? So if you do not specify bins, okay, so if bins is just null, then here you will have a plot, okay, that will use the bin width, okay? So I'm again calling this here bin width because that's the name of this variable in the function input. So that's why here I'm using the same name. But obviously in the function, you would just call it something like bin width equals 0.5, okay? And then I will know that it should just use 0.5 here. If, however, you have not specified the bin width, but you have specified the bins, so the number of bins, then R will run this part here, okay? So it will check if the bin width equals null. And if this is the case, then it will run the part here where it uses the bins, okay? So you just specify bins equals 10, and R will know that it should use 10 here, okay? Good. You can call these variables however you want. You can also call them my bin. You can call them number of bins, however you want. It's just important that you use the same name here and the above, okay? Good. And then basically R will do all the rest. So it will create these first plots here, depending on your parameters. So either using bin width or the bins. And then it will add all the other bits and pieces to your histogram. Okay, so it will add the density function representing the normality curve. Then it will add the summary statistics as lines. It will change the theme to theme classic, do a little bit more on the aesthetics, add the labels, and so on and so on. And also here, we're going to then extract the x-min and x-max, so the range of the x-axis. Then we are making the box plot, exactly the same code as we had it before. By the way, in both cases, we are using the variable lab here. Okay, so we're using it here for the title, and we're using it here for the x-axis. Okay, so that's the name that you give to your variable. So the nice label. Okay, in this case, bill length in millimeters, and so on and so on. And then we have the QQ plot here, exactly the same code as I showed it before, and also using the variable lab here in the title. And then again, the same code as before, we have the text here. And then again here, for the output now, depending on what you specified in the input of the function. So if you specified print to equal true, or basically you didn't even specify it because that's the default. So then R will first print the text into your console, okay? And then it will make this empty plot here, combine histogram and boxplot together, combine the QQ plot with the empty plot together, then combine all these plots together and save them as all plots, okay? And then if you specify print to equal false, then R will combine the histogram and the boxplot together, the QQ plot and the text plot together, and then combine all these plots together into all plots, okay? And at the end, and this is also a very interesting part in the function, what you want to have as the actual output is a list that has all of these elements. Okay, I already mentioned in one of the very first videos that in a list you can basically put everything. And you can have a named list, which is exactly what we're having here. So this list has 5 elements. The first element is basically the histogram. So that's why we're calling it here histogram. And then just adding here the actual object name for our histogram plot. Then we have the box plot, the Q plot, so that you can assess these individually if you need to. And then we have all plots together, okay? And then we have the summary statistics. So if you want to save them as a CSV file, or you want to calculate something with them, or you want to use them for anything else, then you can assess them here. Okay, I can also show this afterwards. So this is the function. As I said, we already went through the entire code while we were using the first script here. Okay, so I'm not going to go more into detail. I'm just going to quickly save this because I've just made a few changes, but nothing really significant. And now we can go back to the actual script here. Okay, so the first thing that we're going to do, and I will demonstrate this quickly, we're going to go to Files here, to the working directory where I'm currently working in. And then I will create a new folder, which I'm going to call the ggNorm figures. I'm going to scroll until the end, just to show you that this is going to appear here at the very end. Okay, so I'm using dir create to make a new folder, and I'm going to use this folder to basically save all of my output. Okay, good. Then I'm calling the function. So far, I haven't done anything with this function. Okay, we've just wrote a function and we saved this as an R script, and it's in the very same folder as everything else. Okay, so it's in my working directory. And you can see here, we do not have it in the functions. But now I'm using the function source. And the only thing you have to do is to add the name of your script here. Okay, so name the script function ggNorm, and it has the extension .r. And if you run this, then it gets you this function here into the environment. And you also see here that this function has many more of these variables that we're using as the input compared to other functions that we wrote. Okay, I've just quickly cleaned the console. So before we start writing the for loop, just a quick explanation what we want to do. So as I said before, we have this penguins data set that has 3 different species on 3 different islands, 2 sexes, and we have in total 4 variables. Okay, what you want to do is that you want to check the normal distribution of each of these variables for each of these groups. Okay, So one group would, for example, be the bill length of adult females on the island Torgerson, like we just had it, okay? So I want R now to run a for loop. I'm pretty sure there are other ways, but we know for loops are cool. To run a for loop that will look into every level of the species factor, into every level of the island factor, okay? In this case, species specific, okay? And then look into every level of sex and into every level of variables. And for each of these data groups, okay, so subsets of your actual data frame, it will run the function that we just created, okay? Good. So, and this is just one way how you could do this. I am first specifying all levels of the factors that are going to define the subsetting of my data, okay? So I want to have all species, so we're just using unique here, and then assigning this to an object called all species. And we see here that all species is Adderley, Chinstrap, and Gento. Then we have the sex here, and then we have the variables here. As already said, not each species is found on each of the islands. So that's why we are going to define the islands within the for loop. Okay, again, there are different ways. You can just tell the loop to skip whenever it comes to an island where we do not have the species. Okay, but we are going to do it a little bit differently. Also, I want to have specific labels for the variables. Okay, I do not want to have bill underscore length underscore whatsoever. I want to have nice labels. Okay, labels that you would also put on plots that you're submitting within a manuscript, okay? So first, let us check the variables here. So we have bill length, bill depth, flipper length, and the body mass. So the labels should then be bill length in millimeters, bill depth in millimeters, flipper length in millimeters, and body mass in grams, okay? So we just make a vector and call it labels here. And then in the next part, I am using the as list function to make a list out of the labels, okay? And then I'm setting the names of this list to equal to the actual variables, okay? Just gonna quickly do this and show you how this looks like. So this is now how this list looks, okay? So the name of each element is the actual variable as we have it in the data set. And the element of each list is then the actual label that you want to use for this variable. Okay, good. Then we can specify any of the parameters that you want to control. So in this case, I'm just going to use the bins rather than the bin width, and I'm going to specify bins to equal 10. And because I want to export the figures for each of the variables, I am going to specify the width and the height of these figures. Also, again, something you might want to play around with, but I'm just going to specify it here to be 12 for the width and 7 for the height. And now we have this loop. I'm not going to run the loop yet, but I'm just going to show you the different elements of the loop, okay? Again, I can't emphasize this enough. There are definitely different ways of doing so, okay? This is just something that I think is understandable and gives you a feeling for the loops and works, okay? And that's the most important part. Definitely remember this. I know for myself, I'm super judgy when it comes to R scripts. I definitely am, I know. But in general, whatever works for you, where you feel comfortable, where you feel certain that this is correct, then that's exactly what you should use. And that's the script you should write. And that's the script that you should feel okay with, okay? There are always better codes than whatever someone wrote. I'm pretty sure someone else can basically get this code into half of the lines that I use. Pretty aware of that. But as I said, this works good for me. I understand what I did. I understand it in a way that I can explain to someone else. At least I hope so. So that's why we're going to stick to this first. Okay, good. So we're going to have in total four for loops. Okay, so we have the first for loop here, the second one, the third one, and the fourth one. In the first loop, I want R to basically subset the data into different species. Okay, so I'm just telling it that for each I within all species, okay, so I in this case is going to be Adderley, Chinstrap, and Gento. It should subset the data set for these species. So we are basically creating a new data frame that only has these species of interest, okay? And then, and this is important part here, we are looking for all islands on which the species occurs, okay? And this is why we have to do it within the for loop here rather than outside, because we know that not all of these species are found on all islands, okay? So what I'm doing here, that I'm taking this new data frame and using the function unique to find all unique islands, okay? Good. And then I'm saving this into an object here. And then in the next loop, I want to have the data set subdivided by each island. This for Chinstrap and Gento is not even important because they only occur on one single island. But for Adderley, this is important because Adderley occurs on all 3 islands. Okay, good. So similar to before, we are just subsetting the data frame. In this case, it has to be the data frame that only has the species of interest, obviously. Okay, so we're just taking the original data and then we're getting always smaller and smaller and smaller until we get to the data set that has only the variable with all the other conditions that we're interested in. Okay, so we're taking the DF species and filtering here to get the data that refers only to the island of interest. Okay, then in the next loop, we're doing the same for sex. Okay, so we are now using the DF island here and then subsetting it by female and male. And then in the last, and this is the most inner loop, that's where all the other stuff happens. Okay, so keep in mind that usually the most inner loop is the important one because that's where all the other process is happening. So here we are using M in all variables. Okay, first we are creating this variable. Okay, and we're not using the pipe operator here because if you would use the pipe operator here, then we would get a data frame, which also works. But currently our function is written in a way that we're using just a vector for the variable. Okay, so here I'm going into the data frame sex, into the column value, and basically only extracting the rows that have the variable of interest here. Okay, and then I'm creating the variable name here. As I told you before, we have this labels list that has all the labels. And the only thing you have to do here is insert M here, okay? Because, and I'm going to just show this quickly, we said here that this list has the names that equal to the actual variables, and then the elements of the list are the actual labels. So if we just do the following, so labels list, and then we use the square brackets here, and then we just write bill length in millimeters. This gives us the actual label. Okay, so this is exactly what we're doing here. And then we're pasting all of this together. I'm using the pay 0 here, which removes all the spaces. So I'm just introducing some spaces where I really want to have them. So we're going to have the name of the variable here. So for example, bill length in millimeters, and then in, and then I here stands for the species. So that's the running index for the very first loop. Then we have K that refers to the sex here. Okay, so we're going to have bill length in millimeters in Adderley females. And then we have the parentheses here. And in the parentheses, we then have J, and J equals the island. Okay, good. And then what we're going to do is just to run our function. Okay, so we have now the variable x, we have the variable label. Okay, we've already specified the bins even before the function. Okay, and we here are specifying print to equal false. Okay, because we want the text to be printed in the figures directly rather than into the console. Okay, so this is the function that we're running. And we are saving the output of this function into diagplots. Should stand for diagnostic plots. And this is then just a list that has those 5 elements that I've mentioned in the function before. So this is this part here, okay? And as a list, you can also just assess these elements by just typing diagplots and then the $, and then each of these names here, okay? And it will exactly give you the element behind it. Okay, and then here we're specifying the file name for the figure that we want to plot. And it's important here to use pay0 and then to specify the folder where we want to save all of these figures. In this case, it should be the ggNorm. And we're including here the variable name. So that's the one that we're specifying here, and adding the extension PNG so that we know that it should be a PNG. Okay, and then we're just using the ggsave with this file name. And then we are here using the diag plots and then the $ all plots. So it's going to take all of these plots combined, okay? And we already specified the width and the height before we wrote the loop, okay? And that's already it. So that's done. That's the 4 for loops. Now I'm going to quickly demonstrate this. I'm going to go into the ggNorm figures folder and run the for loop. And we see here that these figures are now appearing, okay? I really find this very nice to have this both happening. So looking at the code and seeing it all happen here. So I've skipped some of the video material so that this doesn't take that long. Okay, so we see that everything is done. We have all the figures that we need. You can open them, you can look into them. You will see that maybe the size is not perfect, but you can adjust that. And we're done. So yeah, thank you for listening. I hope that this was helpful. I hope that this was understandable. If not, you can always drop me an email. You can leave a comment or anything else. Thanks for sticking with me for this entire period of our series. I'll be happy to do a few more videos next year as well. But I think that for now, we have covered a lot of the stuff. There is a lot of video material that you can watch and rewatch. And as I said, if you have any questions, I'm very happy to answer them. And just let me know. Thank you. Bye bye.